Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to this talk. It's my great pleasure to welcome Matthew Flatt from the University of Utah to talk to us about continuations, I believe. Okay, thanks.
Thank you. Great, so let's see, how many Scheme fans do we have in the audience? How many continuation fans? Oh, this will be an easy talk then. Okay. So where this all starts is basically Scheme provides first-class continuations. It's part of this, the typical language, what people call Scheme. And also people noticed, especially Christian Connect noticed around 2000 or so, that continuations give you a way of writing certain kinds of web servers, web services. And that's where I come in. You know, I build a Scheme system. People use it. They use it to build web server. And then after a while, what we noticed are that Scheme continuations really don't quite work the way you want. Continuations as they are in Scheme. And I'll show you what I mean. This is an example of why people think continuations are useful for some web services. Now Ajax does a lot of the same kinds of things, and what practitioners that I talk to, they tell me you want a mixture of these techniques. But just imagine that you're going to do all this on the server side. You're going to ask the user for some search terms, right? And then once you find out the terms, then you'll go do some search in a database, and you get the answers back, and then you feed the user back those answers. So the way I've written it here is the way you would write it in direct style. If you have a GUI toolbox sitting on your machine right there, or you use a terminal or something, you call this subroutine, get search terms, it gives you an answer back, and then you go find the answers. But in a traditional kind of web server setting, what happens is you have to send back the user some sort of form here to find out what the search terms are. And then they're going to send you back another request later that gives you the answers, and then you continue from there. And what continuations, having them in the language let you do, is still write this little servlet just in this direct style. So here's what happens when you implement it. Your web server is going to accept some TCP connections in and out and pass them off to some serve function. The serve function actually is going to more specifically build up this kind of computation. It's going to say, generate HTML based on the input stream, so find out what they're asking for, generate the appropriate result, and then send it back out, reply back out to the out connection. And since I've got this nested expression here, I'm going to break this up and draw the picture this way. So there's a little square box now at the top where there used to be the sub-expression. That's a placeholder. Let's see, like this. That's a little placeholder that says when you get a value back from that sub-expression, put it in here and continue. Right? And then this is in the square box is the current expression I'm evaluating. So you could call this the continuation up above, or you could call it the stack. Right. Generate HTML, what does it do? Well, it parses from that input stream, and but before it does that, really, this is part of using continuations in a server. I'm going to grab the current continuation and bind it to this variable escape. And then I'm going to do the actual dispatch on whatever n says. So call CC is grabbing the current continuation, that is everything above the box there, binding it to escape for use later. Okay, this is actually the boring half of the continuations, but it's a half we need. Then we continue on with the dispatch. Okay, and now dispatch goes along, and then it says, they want to do a paper search, let's go run this servlet that asks for the search terms and then does the searching. And this is the servlet written in direct style. And okay, what we've got here is, again, a compound term with a sub-expression to evaluate it. So we leave a little gray box there and continue on getting the search terms. And then this is where the more interesting half of the continuation happens. Because again, this servlet is going to grab the current continuation, which is what to do after you get some search terms back. So this is the continuation we're going to resume to later. We've bound that to WebK, and what we're going to do with WebK is somehow translate that continuation into a URL that we can use. When someone hits this URL later, what they mean is they're supplying a value back for that query. Okay, so we're going to take that URL, we're going to embed it in some form that actually gets the user's search terms. Right, so now we've built up an HTML page that has this URL as what you do when you submit the form. And now this is where we use escape, because rather than continuing finding paper terms right now, we need to send this form back as the result. So we invoke the, we've grabbed it. We build the HTML page that has the form in it, which has inside of it the URL that represents WebK. And now we escape. That is, we restore that continuation that we saved over here, putting that web page in as the answer. And then it goes on. Okay. And then when we get another request later when they submit the form, right, this is out to and into, a second connection, a different connection than the out one and in one that we had before. And as we dispatch on that, what we eventually get to is that URL represented WebK, and we also parsed out of the URL the form answers. Okay. And now when we apply WebK, what that means is we apply this continuation to that argument. What does it mean to apply a continuation? Well, that means we're going to throw away the current continuation, the stuff above the box right now, and replace it with this continuation that we saved. Okay? Which is good in the sense that that continuation says, take those form answers and start searching. But there's a problem with this picture right now. And that problem is that once we do find the paper search terms, we're going to reply to out1, which is what we captured in our continuation. And that's wrong. That's the old outgoing connection. We need to reply to out2 instead. So this is just an annoying little problem, and you can think of ways to fix this. Instead of remembering out1 or out2, you have some indirection, or you somehow return the connection that you need to reply to. But there's a much better way of looking at this. And that is to say that really we didn't want to capture the whole continuation. We only wanted to catch the part that is the servlet. And people have thought about this for a long time. There exists already this notion of a delimited continuation. So I'm not going to use escape anymore. I'm going to use prompt. And prompt is just something that when it gets a value, it returns it. But mostly it sits in the continuation, or it sits on the stack as a marker. Right? It's a prompt in the sense of a prompt at the Unix, a Unix prompt or a read-eval print loop prompt. And so dispatch in this new version of the server is going to go on the same way as before. This time, though, when we capture WebK, call CC stops when it gets up to a prompt. So it's only going to capture this much. That's why it's called a delimited continuation. It's delimited by prompt. And the other half of this is we didn't use escape anymore. We have this other operator, abort, that just aborts to the current prompt. So we're breaking up some things here where we used to have capturing continuation and using that continuation to abort. Instead, we have separate ways of capturing and aborting a continuation. I'll talk about why we break that up. Right? But they're smaller, simpler operations, so you can see why that might be a good idea. Anyway, when we abort, that means we throw everything through the prompt, and then we reply out1. Okay? And then this time, when we get that second request, the one with the answers, when we do the dispatch, again, it's going to say WebK form answers, which again is going to apply the continuation. But this time, this continuation doesn't replace the whole continuation. It only replaces up to the prompt. And there's nothing actually between the prompt and the box, so it doesn't replace anything. It just extends it in this case. And now you see that the right thing is happening. So form answers is going to go there as the result. We got the answers back from the users, and now we can continue computing and find the paper. And when we get an HTML page from Find Papers, that's going to be sent back to out2 like it's supposed to. Okay. So what could be easier, right? Continuations seem to make your life easier. Delimited continuations encode it more cleanly. And in fact, in my experience, any application of continuations I can find, the limited continuations are slightly cleaner. Right. So it's a little bit better programming model. And you can simulate delimited continuations by using call CC and bouncing around in certain ways. Right? So you can simulate prompt and you can simulate delimited capture of continuation. But if you simulate it that way, if you put it in a library or something, then that simulation is not going to work with all the rest of your language, like exception handling or dynamic bindings for dynamically scoped variables and things like that, or dynamic wind, which is a kind of generalized try-catch mechanism. So, what we set out to do is to give you delimited continuations in the programming language and figure out how it works out with all these other little things. And that's really the main contribution here, is just figuring out how to make this practical. Because after all, lots of people have thought about delimited continuations. This is not a complete list of all the papers on the theory of delimited continuations and why it's probably a good idea and how it cleans up all your proofs and how it's easier to reason about in general, in much the same way that we saw in the web server example. Okay? There have been quite a few of those papers actually specifically address what's the right constructs to give to programmers. What's a good set of delimited control operators to give them. A couple of those papers actually go so far as to try to implement the thing. They say, if you got a real implementation, here's how you would drop it in. Gauss, Bickler, and Sperber did it for Scheme 48, and Dybvig and all talk about it in Scheme, one particular Scheme system, and how you would encode it in monads, of course, for Haskell. Yeah. And then, if you actually want to go download an implementation, well, that was your list of choices there. Well, until now. Now this is your list of choices. So there's one implementation that actually gives you delimited continuations and mixes it with all these other constructs. Why only one? Okay. If people have known about this and bothered to write dozens of papers, well, because you really have to, as I was saying, integrate it through with the rest of your functions and constructs. And in particular, it's very easy to make continuations, delimited continuations, too powerful, so that users and libraries, libraries can interfere with other libraries by using continuations in a bad way, the same way that simulating delimited control doesn't work. So we want to avoid this situation, and that's what the paper is about, is providing a comprehensive design for delimited continuations in Scheme. And we provided a formal model for that, and as I said, you can go download the implementation. In some sense, this talk is about none of those things, because really what I just want to give you is an intuition for how it all fits together. What are the issues that are involved? And maybe the graphical intuition is as much a contribution as anything. Just a way, as you saw at the beginning, those pictures for understanding what continuations do, I will use those pictures and develop it more precisely. So that's really what the talk is about. And the intuition also kind of bridges the gap between the design and the formal model, because there's a close correspondence between the pictures and the Greek that implements it in a normal operational semantics. Before I go on, this is a great place for questions? No? Okay. So let's start building up this notation again, which I've kind of explained, but I'll explain it more now. Suppose you've got a scheme expression like this. So this says v1 applied to the application of this expression to v2, where this expression is the identity function applied to 3. Okay. As this is going to evaluate, the first thing that can happen in scheme evaluation is that we need to apply the identity function to v3. So that is the piece that I would put in the square box at the bottom. And the next piece out says whatever you get from that, you apply to v2. So that's the next piece there. And whatever you get from that, that becomes the argument for v1. Right? So if you're doing an operational semantics, you provide a certain grammar that breaks things up in this way. And so that's why there's a correspondence between that and this picture. You can see where it comes from there. So we're going to draw the pictures, and then we're going to talk about the reduction rules on these kinds of programs as manipulations of the picture. So if this is your program, and you might as well represent it using these bubbles as well as just plain text, then the way it evaluates is, well, you've got some rule that deals with the core things, like beta substitution here. Okay, so you do a beta reduction, and you're going to get v3 out of that. And the way we continue with the picture then is to take that value and put it in place of the faded square brackets, which I'll call the hole. Put those in the hole back in the continuation, And then the continuation becomes the expression to evaluate. And, well, let's back up. And let's suppose that instead of a simple function call, we have call CC. How does that evaluate in picture terms? Well, as we saw, what it means is you take the current continuation, make a copy of it, and then I put it on the side and kind of loosely gave it a name before. But what really happens is this thing goes in for k, which is to say that this continuation replaces k in the body of the function here. So in picture form, that's what you'll see happen. The k will fade away, and now you've got that continuation applied to v3. Now we have a continuation application, so we need a rule for how to continue from there. And the rule is you throw away the current continuation, you put this one in its place, and then you take the argument, and that becomes the value that you feed back into the continuation. So that's all continuations are pictorially. Taking the intuition of a stack, which is really corresponds closely to the stack of bubbles. Okay, so that is continuations as they exist in Scheme. That's plain call CC, was how we captured the continuation and how it applied. But a lot of that literature that I listed there before is about composable continuations, which I'll represent by drawing a little green arrow at the top of my continuation. And composable means that when I apply this continuation, it does not replace the existing one. Right? So when you apply a composable continuation, it extends the current continuation, or composes with it, which is why it's called composable. And then this computation would proceed as before. Right? V3 goes in as the argument. You rarely hear about composable continuations by themselves, though. And here's why. If you have a real program, then that last frame, the deepest frame in the stack, probably says exit the program. So if you capture the entire continuation, well, and try to splice it into the middle of the continuation, it does you no good because you just splice in exit the program. And so none of these other things will happen. So the piece that goes along with composable continuations is delimited continuations. So these things go together and they naturally work together. And we saw that before. In the example, we use prompt to delimit it and call, instead of call CC, I'm using call comp here to capture a composable continuation. And so that's going to capture just that middle bubble. And put a green arrow on top because it's a composable continuation. All right, so we have several pieces at this point. We've got, and then when this applies. Just the last piece we've also talked about, the abort. Since we're splitting out composing a continuation versus replacing the other one, it's natural to have a separate abort operation, as we saw, that finds the closest prompt and then throws everything away through that and then returns the value that you give. Okay, so this is the summary now. What we really added are call/comp, that is, grab a composable continuation. Well, we also added prompt, which isn't on the slide. And we added board. The reason that these two parts are on the slide is because the classical representation of these was called F, this script F. And it combined both of those as the same operation. Now, why do we bother splitting them out, or why was it put in one operation before? Well, the reason it was put in one operation before was it was from theorists who like to have one when they can have one instead of having two. We're going to have a practical reason for splitting them out. Unfortunately, I can't really explain that until we've gone through a bunch more. So just for the moment, take my word for it, it's better to split them out. What you would like then is you can get back to F if you want. And actually, you can't yet. We're going to need one more ingredient. So the problem is, the way F works is you grab the composable continuation and you abort. But after you abort, you do some more work that someone supplied. Right? And in that more work that you do, you're supplying the continuation you've done. So this is the part we can't really do here, this delayed application of F applied to K. If we tried to apply F to K directly and then send that result to abort, that's too soon because we haven't actually done the abort yet. So to have enough little pieces that you can get F back, what we want is a variant of prompt that has a handler. So this handler is going to be used whenever we abort. When we abort to V3, instead of throwing away the prompt, we're going to throw away everything up to the prompt and then feed v3 into this handler procedure here. So this is a slight generalization of prompt. Right, so that's just pictorially what I was saying. And then when we have that, and let's just agree that if we omit the handler, what we mean is take any procedure and just call it. Take a thunk here and invoke the thunk. So that way, if we use this notation, then you get f back. And then f works by calling abort, assuming the default handler. If you look at this, surely you thought, well, this is actually called catch and throw. Okay. Because I'm setting up a catch with a handler, and then I'm aborting straight to that handler. And that's true. Of course, we're going to be able to use these pieces for more general things also. But we would like to just use prompt and abort to get catch and throw. And you can do that. You can just rename them. But then, what if you had a program like this? So suppose you do a catch, and then you set up a prompt so that you can delimit continuation. And then you raise an exception. What should happen? Well, unless you were a language theorist who wanted to think about throw and catch and implement it in terms of prompt, really you want these to be different kinds of things, right? But if catch and throw are just aliases for prompt and abort, then the throw is going to the wrong place. Okay. So your exception handling probably should not be mixed up with your continuation capturing. At least if you don't want them mixed up, then we need one more ingredient. And it's a simple one last ingredient, a tag on the prompt. So every time you set a prompt, you give it a particular tag that says which kinds of continuations, which kinds of aborts you're capturing. And then now we say abort with vxen, which is going to abort all the way up to there, because that's the prompt with the matching tag. In contrast, if we had different prompts with different tags here, first thing that's happening here is I'm capturing a composable continuation with tag 5, so we capture that much. And then I'm sending that through abort to tag 4, which means we abort to that much. So nothing particularly surprising there. But these are all the little ingredients we need to make things work out nicely. Okay. And in fact, these ingredients were already worked out. Right? In that big list of papers was one Sitaram 93. That is essentially the set he came up with. Okay. So in one sense, we're taking that work and putting it into practice now. Minor detail here is, again, he had F, which was combining the two things. We're splitting out abort with call count. But he already had the right generalization in there with prompt, with tag prompts and with prompt handlers in order to get F back. Okay. So we're really essentially using that design. And you can fit call CC into the model here. You just say it's using some default tag. Okay, any questions now? Okay. So all I've done now is sort of remind you what continuations do and claim, hey, that paper, that was the right one to implement. We have a bit more work to do in our setting on how to integrate with some other things, in particular dynamic bindings. And the way dynamic bindings, you would like to think of them as you attach some bindings like V7 is bound to V12, attach those to continuation frame. And that works out. In fact, we had generalized this already into a notion of continuation marks. And so we just need to work out the details of how continuation marks and composable continuations operate. Obviously, when you capture this bit of continuation, it should just remember the marks associated here, not anywhere else. And this was another little detail that was mostly worked out already by a paper just a year before at ICFP. That was, I think, Kizoryov and Shan. There are some extra details having to do with tail calls and overlapping frames and so on. But details. We'll leave that to the formal model in the paper. There's one more thing which was a more serious issue and was the real obstacle in terms of getting delimited continuations in the scheme. And that is what you do with dynamic wind. So dynamic wind is for settings like this. Suppose you have some abstraction, some library call with resource for some particular resource, say a file. And then you supply that a thunk that's going to do the actual work. where inside of this library you grab the resource, then you do the thunk, and then you release the resource. Okay? So this prevents you from forgetting a close after an open or something like that. What if work thunk raises an exception? Well, you want to close on that case too. What if work thumps jumps out through a continuation? Well, maybe you want to close on that case too. What if work jumps out through a continuation and then somebody jumps back into work thunk through another continuation? But then you need to reclaim the resource as you go back in. In Scheme, the job for doing all this is dynamic wind. So dynamic wind tells the runtime system, cooperate with continuations anytime you get into work thunk, either by normal flow going in or by continuation jump going in. Make sure you grab the resource. Make sure you do whatever this first thunk says. Whenever you jump back out, you return back out, whatever, then you need to release the resource. And the general form here is dynamic wind takes three things, and I'll call the first one the pre-thunk, and the last one the post-thunk, and the middle one the body, which you're trying to do. So the body is protected by the pre- and post-thunks. Okay, so if we put this inside of a program, then we need to give the reduction rules that say how you evaluate this. So we get down, our program's computed, now we've ended up at a dynamic wind call. We've got three thunks here. What's going to happen is dynamic wind is going to turn into a DW frame. And the DW frame is going to start evaluating the body. And as it does that, the way that we're going to write DW with a hole in between is just a special way. So we're going to use this particular notation to highlight the fact that dynamic wind is doing something special for continuation. These little spurs are supposed to be things you have to deal with if you're jumping in and out. Right? When we have just plain bubbles, a continuation can throw them away. When you got spurs on them, you can't just reach in. You have to do some work first. The spurs protect it. When you're jumping in here, you have to do the pre, and when you're jumping out, you have to do the post. That's where we're trying to get. Actually, I've skipped some details here, because before we do body in a regular computation, we need to do the pre-thunk in that case too. So what actually happens is DW, dynamic wind doesn't go straight to DW. It goes to a begin with a hole and then a DW. So when you reduce the dynamic wind, you set up this pattern where you start evaluating the pre-thunk. Now, while we're doing the pre-thunk, there's no spurs yet. Right? And this corresponds to something that people eventually figured out, which wasn't obvious at first, that while you're doing the pre-thunk, you shouldn't do the post-thunk if you escape. Or if you capture a continuation in the pre-thunk, there's no more pre-thunks to do to jump into that. At least no new ones here. Okay? So we can make that clear with this particular reduction rule. And then once you get a value for the pre-thunk, what happens is that value goes into the hole for begin, and the evaluation rule for begin says, well, just throw away the first value and then continue. Now we have this dynamic wind thunk, which we draw with the spurs, dynamic wind node rather, DW node, that we draw with the spurs. So now we're down to evaluating the body. Suppose that that body is an abort. What's going to happen? We want to jump out back to some prompt that I haven't shown here. I've omitted some of the continuation. But to do that, we have to deal with this spur, the post spur. And the complementary thing can happen if somehow you grab the current continuation at this point and you apply it later. So we're jumping back down into this. Then in those cases that we're jumping back down, we also need to deal with the incoming spur in that case. So the orange lines are showing something we have to deal with. They're not part of the reduction notation. This is an intermediate intuition for what needs to happen here. Okay? So is everyone with me on dynamic wind? That's its job. These are the kinds of issues we have to deal with. And we have to deal with them in the delimited case. Okay, so how does this work? That orange line represents some idea of how evaluation should go. I need to turn that into rules that manipulate the picture. And so the rule is you take the thing that you hit with the spur, you throw away all the pieces except the post, and you remember that what you're trying to do is abort. But before you continue aborting, you need to run the post thunk. So when we're trying to escape and we see a spur, we rotate the picture around this way. And of course, eventually when we get the post value out, then we're just going to continue on and continue with our abort maybe we hit some more spurs, or maybe we're able to go straight ahead. Great. So this is the bigger, more complicated case. Dynamic line and call CC. So this is the existing scheme call CC that in order to be practical, we still have to work right with this, along with dynamic line. Okay. So let's say you have a computation that looks like this. You got a couple of layers of dynamic lines. Maybe they're protecting files or locks or some other resource. And at this point, you grab the continuation. So we're just grabbing. We're not jumping inside or out. So we don't have to remove any bubbles. The spurs are OK. But we preserve the spurs, of course. And let's say this computation continues in such a way that the K eventually goes out here. And then the stuff around the dots eventually causes the computation to look like this. So we leave one dynamic line normally, and then we enter a new one normally. You can see there's E5 and E6, not E3 and E4. This is a different dynamic line. In fact, from the scheme programmer's point of view, the way they're thinking about it is probably like this. They started doing some computation, and then they said, oh, this is not working out. Maybe it's some sort of search. And they backed up, and then they went down this other path. Or in a web context, maybe they were here, and then the user hit the back button, and then the user went back down this path somehow. So in the scheme programmer's mind, they're exploring this particular tree of computation with continuations. But these trees, we don't have trees. We have chains. This is our notation. So we want to make some connection between these chains and the tree that's in the scheme programmer's mind. And in particular, if the computation gets down to this point, and this is where we're going to invoke that continuation, from the scheme programmer's point of view, we're going from this part of the tree over to that old part of the tree. I had it backwards before, actually. The program did this, and then we came down here, and then from here we're jumping back over there directly. Right? So in the scheme programmer's mind, again, they're only going to deal with these two spurs, this particular post-thunk and this pre-thunk, not go all the way to the top and all the way down. If you just look at our flat chain over there, though, it looks like you're going all the way out and down into another one. So we have to adjust the rules for what it means to draw the orange line, which in turn is our intuition for manipulating the pictures, to take into account the sharing that was in the scheme programmer's mind. And the way we do that is we need a way to recognize that these two are in fact the same prefix. Right? And when we can do that, then we can say, okay, the rule for drawing the orange line is first you find same prefixes, and then considering only the part that's not a prefix, that's where you draw the orange line. And in order to do that, actually, it could happen that you did the same dynamic line frame with the same pre and post thunk, but it was different explorations. So we add on the dynamic line nodes, the DW nodes, a little tag that corresponds to the runtime instantiation. So if you do the same computation twice, and you jump from one to the other, that's jumping all the way out and jumping back in. And you can tell because you would have generated different tags. Okay? So there's a lot of machinery here, but you can fit it into this notation, and you can see where it all comes from. And then you can take this and you can map it down to the formal rules, and you can take the formal rules and map it down to an implementation. Or at least run the formal rules as a test oracle against your implementation, which is what we did. Okay, so that's all the machinery you need to do this. And then what's going to happen is you see that orange line being drawn. So we had, similar to the abort rule, these are the transformations. You do that post-thunk that you're supposed to do, and eventually that gets a value. And then you continue on. And then again, what happens is you have a continuation jump. It's jumping over here. So you find the common prefixes. You discover that the next thing to do is the spur. Turns out to be important to do exactly the way I said. You can't pre-compute the orange line and then try to go through them all because, well, a pre and post thunk may manipulate the continuation in such a way that your pre-computed orange line is not correct anymore in the future. So you really have to do it this way. Each time compute an orange line, find out the next step, just do that next step, which is reminiscent of these local rotations. So that's what we worked out and spelled out and described with these pictures. And just to summarize there, the notion that there is an identity, a runtime identity associated with the dynamic line frame. What it means to have call CC in this world, and how dynamic line thunks are captured when you capture different kinds of continuations. Exactly how the post and pre thunks are evaluated, And I note that there are details here that I mentioned. Do you evaluate a pre-thunk if you're jumping out of a particular post-thunks continuation into another pre-thunks continuation? Right? Details like that are all addressed correctly in the pictures. And people didn't know how to do that at first. We eventually decided it probably should work like this, but we didn't pin it down very well. Now we've pinned it down. Okay. So that's all I have planned to talk about here. If you want to follow up on this more, there's the paper that this talk is based on, and it goes into a bit more detail on continuation marks, for example. There is the formal model. That is the Greek version, well, the scheme version of these pictures. Right? The scheme version that looks like Greek almost. And then, of course, you can download the implementation. Try things out. And with that, I'll take some questions. How could it be any other way? Chris?
So, what applications have you used for this so far?
Good question. The web server is in fact the main application so far. So the web server does use it. It cleaned up some implementation. It cleaned up some performance problems. It cleaned up some leaks, perennial leaks that we had not worked out all the right out1, out2 in directions. One other example is actually in building slides like this, where you have a picture that morphs into another picture, and you want to compose those different kinds of pictures, and you want a nice programming style. You can encode nice combinators through continuation. So you describe your picture as a function that takes a number between 0 and 1, and then you want to be able to compose these kinds of pictures and then feed those into the main driver that goes from 0 to 1. A Haskell programmer would say we're using monads, but we're expressing the monads through delimited continuations in that case. I did not figure that out. After I had this talk, I gave this talk, Ryan Culpepper said, you know, actually, delimited continuations are what you need to build combinators over the picture about your talk on delimited continuation. So. Small examples. If you ask me what's the application of continuations, period, I would give you the same answer. I think certain kinds of web services are the main reason continuations may be useful, as far as I know.
Do you think you can transfer some of these concepts outside of scheme?
Sure. So yeah, all of these will work in other languages. And in fact, if anyone is thinking about adding first-class continuation support to a language, you should add delimited continuations, because they're what programmers actually want most of the time. I'm not the first person to say that, of course. Many other people have said it. It's all a long list of papers. There's now that we've worked out the details of exceptions and other things like that, there's less of an obstacle, perhaps. It can be challenging to implement depending on your existing architecture. Okay. Thank you.